Welcome to the Deep Dive. We're here to plunge into fascinating topics, pull out the key insights, and bring them straight to you. Today, we're looking at something absolutely fundamental, but maybe something you don't think about too often. Light. Have you ever really stopped to wonder what actually makes things visible?
It really boils down to light reflecting off objects, doesn't it? That's how we see the world.
Exactly. And it leads to amazing things like the colors in a rainbow, or
Yeah.
seeing stars twinkle, or just seeing yourself in the mirror every morning. It's all light. So our mission today is to really explore two key properties, reflection and refraction. We want to unpack how these basic ideas shape what we see and even the technology we rely on.
Definitely. And while we'll mostly talk about light traveling in straight lines today, thinking of it as rays, it's worth remembering light's actual nature is, well, even more complex. Light can actually bend around tiny obstacles, that's diffraction, and it acts like a wave sometimes, and other times more like a stream of particles. Modern quantum theory actually brings those ideas together. It's fascinating stuff. But for this deep dive, focusing on reflection and refraction as straight-line phenomena gives us a really solid foundation.
Okay, good point. Let's start with reflection then. Mirrors, we all use them, but how does a mirror actually work, scientifically speaking?
Well, any really smooth, polished surface, like a mirror, bounces back most of the light that hits it. And it follows two really simple laws. First, the angle the light comes in at the angle of incidence is exactly the same as the angle it bounces off at the angle of reflection. And second, that incoming ray, the reflected ray, and an imaginary line perpendicular to the surface right where the light hits, we call that the normal. They all lie flat on the same plane.
Okay, like they're all lined up on a flat sheet of paper.
Precisely. And the crucial thing is, these laws aren't just for flat mirrors. They work for any reflecting surface, even curved ones.
Right, so let's stick with flat mirrors for a sec, plain mirrors. What about the image you see? What are its characteristics?
Ah, yes. With a plane mirror, the image is always virtual.
Meaning it looks like it's behind the mirror, right? You can't project it onto a screen.
Exactly. It's also always erect upright, and it's the exact same size as the actual object. Plus, it appears to be located as far behind the mirror as the object is sitting in front of it.
And then there's that slightly mind-bending thing.
Yeah.
Lateral inversion. Left becomes right, right becomes left. Why is that? Why left, right, and not top, bottom?
That's a classic question. It trips people up. Think of it less as left-right swap and more as a front-to-back reversal relative to the mirror surface. Imagine you point towards the mirror. Your reflection points back out from the mirror. Your right hand corresponds to the reflection's left hand because the whole image is flipped front to back along that axis. But your head stays at the top and your feet at the bottom in the reflection because that orientation isn't reversed by the mirror plane itself.
Front to back reversal.
Yeah.
Okay, that actually helps visualize it much better.
Mhm.
So what about curved surfaces?
Yeah.
Like, grab a shiny spoon, look at your reflection in the inside curve, then the outside curve. The images are totally different.
Exactly. That spoon is a great everyday example of curved mirrors. We
Yeah.
usually talk about spherical mirrors where the reflecting surface is part of a sphere. If it curves inwards, like the inside of the spoon, that's a concave mirror. It faces towards the sphere center. If it curves outwards, like the back of the spoon, that's a convex mirror.
Okay, concave like a cave, convex bulging out. Got it. Now, there's some specific terminology for these mirrors, isn't there, to help us describe them?
Yes, definitely. Let's break it down. The very center point of the mirror's reflective surface is the pole, usually labeled P. Then there's the center of curvature, C. This isn't actually on the mirror, the center of the big sphere that the mirror is a slice of.
Ah, so it's out in front for a concave mirror, but behind for a convex one.
You got it. And the distance from the pole to that center of curvature, C, is the radius of curvature, R.
Okay, pole, center of curvature, radius of curvature. What else?
There's the principal axis. That's just an imaginary straight line running through the pole in the center of curvature. It hits the mirror at a right angle at the pole. And then, really important, is the principal focus, F. This is where things get interesting. For a concave mirror, parallel rays coming in, like from a distant object, all reflect and meet or converge at this point F. For a convex mirror, those parallel rays reflect and spread out, but they look like they're coming from a point F behind the mirror. They appear to diverge from F.
And the distance from the pole to that principal focus.
That's the focal length, F.
And wasn't there a simple link between the radius and the focal length, something like R equals 2F?
Yes, exactly. For spherical mirrors where the opening or aperture isn't too huge, R equals 2F holds true. It means the principal focus sits neatly halfway between the pole and the center of curvature.
That little formula seems incredibly useful for figuring out where images will form.
It absolutely is. Now, speaking of images, concave mirrors are really versatile. Where the image forms, its size, whether it's upright or inverted, it all changes depending on where you put the object. For instance, if the object is super far away, basically at infinity, the image forms right at the focus. It'll be real, inverted, and tiny.
Like focusing sunlight with a magnifying glass, but with a mirror.
Precisely. That concentrated spot of light at the focus can be intense enough to burn paper. But here's a really neat trick. Put the object between the pole, P, and the focus, really close to the mirror. What happens then is you get a virtual image behind the mirror that's erect and, importantly, magnified.
Uh-huh. So that's how shaving mirrors work, or why dentists use those little concave mirrors.
Exactly. They give you that enlarged view you need.
Okay, so concave mirrors are versatile. What about convex mirrors?
Convex mirrors are much more predictable, you could say. They always produce an image that is virtual, erect, and diminished, smaller than the object.
Always smaller and upright, no matter where the object is.
That's right. Doesn't matter how far or close the object is, the image characteristics stay the same. Virtual, erect, diminished.
Which must be why they have specific uses.
Definitely. Let's talk applications. Concave mirrors, because they can focus light or create parallel beams. You find them in torches, searchlights, car headlights. You put the bulb near the focus, and it creates a strong parallel beam. We mentioned shaving mirrors, dental mirrors. Also, large ones are used in solar furnaces to concentrate sunlight and generate huge amounts of heat.
And convex mirrors, that predictability must be key.
Absolutely. Their most common use is as rear-view mirrors in cars or wing mirrors.
Why are they better than just a flat mirror for that?
Two big reasons. One, they always give an erect image. You don't want to see the car behind you upside down, even though it's smaller. Two, and this is crucial for safety, they have a wider field of view. Because they bulge outwards, they reflect light from a much broader area behind the car.
Ah, so you can see more of what's going on behind you. Makes sense.
It's a huge advantage over a plane mirror, which has a much narrower view. And there are even cool historical examples, like a convex mirror built into a wall at Agra Fort in India that lets you see the whole Taj Mahal in reflection. Quite clever.
That's amazing. Now, you mentioned calculations. Keeping track of distances, object here, image there, it can get confusing with signs, positive, negative.
Yes, so physicists came up with a standard system. The new Cartesian sign convention, it's just a set of rules everyone agrees on. Basically, you measure all distances from the pole. The object is always considered to be on the left. Distances measured against the direction of incoming light are negative, with it are positive. Heights above the axis are positive, below are negative.
Just keeps everything consistent for the math.
Exactly. And that math usually involves the mirror formula. 1 over v plus 1 over u equals 1 over f.
Where u is object distance, v is image distance, f is focal length.
Correct. And we also talk about magnification, M. It tells you how much bigger or smaller the image is compared to the object. It's the image height divided by the object height, h, so M equals h. It also equals negative v divided by u, so M equals v.
And the sign of m tells you something too, right?
Yes. If M is negative, the image is real and inverted. If M is positive, the image is virtual and erect. Powerful little formulas.
Okay, so that's light bouncing off surfaces reflection. What about when light goes through things, like from air into water or through glass? Does it just keep going straight? You've probably noticed weird things happening, like the bottom of a swimming pool looks shallower than it really is.
Or when you put a straw or a pencil in a glass of water, it looks like it's bent or broken right at the surface.
Exactly. Or looking at letters through a thick piece of glass, they seem slightly raised. Or a lemon in water looks bigger from the side.
All those effects are down to refraction. That's the bending of light.
Why does it bend? What's actually causing that?
The core reason is that light changes speed when it goes from one transparent material or medium into another, assuming it hits the boundary at an angle. If it goes straight in, perpendicularly, it doesn't bend, but it still changes speed.
So the speed change causes the direction change.
Precisely. And just like reflection, refraction has laws. First, similar to reflection, the incoming ray, incident ray, the bent ray, refracted ray, and the normal at the point where they meet the boundary all lie in the same plane. The second law is the important one for calculations. It's called Snell's law. It relates the angles. It says the ratio of the sine of the angle of incidence to the sine of the angle of refraction is a constant.
A constant value for a given pair of materials in a specific color of light.
Correct. And that constant value is the refractive index, usually written as in. It's fundamentally linked to how much the light slows down.
So it's a measure of how much a material slows light compared to a vacuum.
Exactly. Light travels fastest in a vacuum about 3 times 10 to the power of 8 meters per second. Huge speed. It slows down in other materials. The absolute refractive index n of a medium is the ratio of the speed of light in vacuum to the speed of light in that medium. So n equals CV. We also talk about optical density. A medium with a higher refractive index n is called optically denser.
Does denser mean heavier, like mass density?
Not necessarily, and that's a key point. Optical density is about how light interacts, not mass. Kerosene, for example, is less dense than water in terms of mass, but it's optically denser, it has a higher refractive index, and slows light down more.
Wow, okay, that's counterintuitive but important. So optical density relates to the bending. How does it bend?
Right. When light goes from a rarer medium, lower in, like air, into a denser medium, higher in, like glass, it slows down and bends towards the normal.
Towards that imaginary perpendicular line.
Yes, and when it goes the other way, from denser to rarer, like glass, back to air, it speeds up and bends away from the normal.
You can see this really clearly with a rectangular glass slab, can't you?
Absolutely. Light enters from air, bends towards the normal inside the glass. Then, when it leaves the other side, going from glass back to air, it bends away from the normal. The interesting result is that the ray coming out is parallel to the ray that went in, but it's been shifted sideways a bit.
Like it took a little detour, but ended up going in the same direction.
Pretty much, yes. A lateral displacement.
Okay, so we've done reflection, refraction.
Yeah.
What about things specifically designed to use refraction, like lenses, think magnifying glasses, eyeglasses?
Right. Lenses are basically pieces of transparent material, usually glass or plastic, with curved surfaces. At least one surface must be curved. Usually both are. They work by refracting light in very specific ways.
And there are two main types, like with mirrors.
Yes. You have convex lenses, which are thicker in the middle and thinner at the edges. They are converging lenses. They bring parallel light rays together at a focal point after passing through.
Like focusing sunlight again, but this time by passing light through it.
Exactly. And then you have concave lenses. These are thinner in the middle and thicker at the edges. They are diverging lenses. They spread parallel light rays out, making them appear to come from a focal point before the lens.
Got it. Converging and diverging. And do lenses have similar key points like mirrors did? Pole, focus.
Similar concepts, yes, but slightly different terms. The central point of a lens is the optical center, O. A neat thing is that a ray passing right through O doesn't deviate at all, it goes straight. The principal axis is still the line through the centers of curvature of the lens surfaces and the optical center. Lenses generally have two principal foci, one on each side, because light can pass through from either direction. We usually call them F1 and F2. And the focal length, F, is the distance from the optical center O to the principal focus, F.
So how do these different lenses form images? Let's start with convex lenses.
Convex lenses are quite versatile, much like concave mirrors. Depending on where you place the object relative to the focus in the lens, you can get different kinds of images. They can form real, inverted images, that's how projectors work, or cameras form an image on a sensor. But if you place the object very close to a convex lens, inside its focal length,
Like using a magnifying glass.
exactly, then you get a virtual, erect, and magnified image. That's the principle behind magnifying glasses and eyepieces in microscopes and telescopes.
And what about concave lenses? Are they more predictable, like convex mirrors?
They are. A concave lens always forms an image that is virtual, erect, and diminished, smaller than the object, no matter where the object is placed.
Always virtual, upright, and smaller. Useful for specific things, I guess.
Very useful. For example, correcting nearsightedness often involves using concave lenses to diverge the light slightly before it enters the eye, so it focuses correctly on the retina.
And there are formulas for lenses too, right? Similar to the mirror formula.
Yes, the lens formula is very similar. 1 over V minus 1 over U equals 1 over F. Note the minus sign there, unlike the mirror formula's plus sign.
Ah, subtle but important difference. 1V1U equals 1F. And magnification.
Magnification M for a lens is also image height over object height, but it's equal to positive V over U, so M equals HH of VU. Again, notice the sign difference compared to the mirror magnification, VU.
Okay, sign conventions are clearly critical here.
They really are. And building on focal length, there's another really important concept for lenses, power.
The power of a lens. What does that mean?
Lens power, P, is simply the reciprocal of the focal length when the focal length is measured in meters. So P equals 1F with F in meters. The unit for power is the dioptry, symbol D.
So a lens with a shorter focal length bends light more sharply and has more power.
Precisely. A convex lens converging has positive power, and a concave lens diverging has negative power.
Why talk about power, though? Why not just stick with focal length? What makes power so useful, especially day to day?
Ugh, great question. It's incredibly practical, especially for opticians prescribing eyeglasses or contact lenses. The beauty of power is that if you place several thin lenses close together, their total power is simply the sum of their individual powers. P equal P1 plus P2 plus P3 and so on, just simple addition.
Oh, I see. So when an optician is testing your eyes, they can just add up the powers of the different trial lenses they put in front of your eye.
Exactly. It makes combining lenses and calculating the final prescription much, much easier than trying to figure out the combined focal length, which is a more complex calculation. And this additive property is also vital when designing complex optical instruments like cameras, microscopes, telescopes. They often use multiple lenses, and designing them based on combined power simplifies things enormously.
That makes perfect sense. It turns a complicated optics problem into simple addition. Well, this has been an incredible deep dive. It really shows how understanding just these basic ideas, reflection and refraction, unlocks so much about how we see how instruments